We are looking at rate laws in this section, how to make them and what they are. So a rate law expresses the reaction rate as a function of reactants. That's what we're all about here. We're all about the reactants, their concentration, product's concentration, and the temperature. It's experimentally determined. So the derived rate law for a reaction must be consistent with the postulated chemical mechanism of the reaction. So here is a general equation, and what we're going to be doing is breaking this down into what is called a rate law. Now we are just interested in the reactants, rate law, maybe that's how you remember it. Notice that we have the capital A, the capital A, the capital B, the capital B, and then we have some exponents. Now these exponents can only be determined experimentally. You'll notice the coefficients small a and b play no part in this. There is also a k. This is a rate constant. The unit's a little wild. The very last thing we'll do in this section is I will show you how to come up with this value. And there's all the stuff that was just said. Okay, so how is the rate law determined experimentally? So first thing we're going to do is we're going to have some initial values that'll be measured in a table, and then there'll be some rates for how the thing went, and then from that you'll calculate the rate constant. Reaction order terminology. Okay, so we got a couple things to explore here. So this rate law here has an exponent of 1. So we say it has a first order reaction. So if we did a little graph of this one, this would be a reaction where, let's say you bought a pop for $1, and then you bought a second pop for another $1, and then you bought a third pop for $3. You would end up with a nice linear relationship here, a nice straight line, and that's what a first order, if you graphed it, would look like. Now the second one here, we've got a 2, and this stands for a second overall, and so this one would be a parabola, and so your increase in reaction rate would be like that. You can actually, and then in our last one here, we've got a 0 order. And for a 0 order, if you did a graph, it would just be a straight line like that. So those are your scenarios. These are how your reactions can proceed. So let's take a look at an example here. Now, just judging from this, we can't really tell anything about the exponents. The exponents were actually determined for this one experimentally, and these were each to the power of 1. So how do we come up with a second overall order? Well, we're just adding those two together. We add the exponents up. 1 plus 1 equals 2. That gives us our second order. Again, these exponents were determined experimentally from some data that we don't have or don't really need for this one, because we're just talking sort of in general at this point. And here's another one. Again, we don't know how this is going to break down, but you'll notice that, again, we've got our reactants here, right? And we've got the oxygen is to the power of 2, and that's the to power 1. 2 plus 1 is 3. This is a third overall reaction. Properties of reaction orders. Reaction orders cannot be deduced from the balanced chemical equation. As I showed you, reaction orders are usually positive integers or 0. They can be half numbers. Fractional and negative as well. So basically they can be any number, anything. So let's take a look at some sample problems. So let's determine the reaction order for the rate laws. So for each of the following reactions, determine the reaction order with respect to each reactant and the overall order from the given rate. So we've got 3 equations that we are going to do this with. There they are. And our first plan is to inspect the rate law and not the coefficients in the balanced equation. So throw those coefficients out. And here, in fact, are the rate laws. Again, these have been determined experimentally. In the next example problem, I'm going to show you how to come up with this, but for now they are determined. All we want to do is just state which overall order they are. So for the first one, you'll notice that we've got a 2 and a 1, so that makes a third overall order. The next one, we've got 3 halves, so that is our order. And in the last one, we've got a 1, a 1. It looks like I'm missing one here, which is also, I guess, the hydrogen. Apparently it's a 1 as well. No, sorry, it's a 0. So 1 plus 1 gives us 2. So there you go. Now on to the more difficult stuff, determining the reaction order. So there's an equation, and this is what we're going to do for the rate law. Again, we don't care about the product. It's not involved here. We've got our oxygen gas, and we have our nitrogen monoxide there. So to find M and N, a series of experiments is conducted starting with different sets of reactant concentrations. The initial reaction rate is measured in each experiment. So let's take a look at the data that results. So now there are some highlighted values. What we need is some consistent values to go ahead and determine some values here. So when we're talking about oxygen, you'll notice that we actually have 3 trials where oxygen is the same value, and that will allow us to explore the numbers that go with the NO. We also have our initial reaction rates that are going to come into play here. Along the other end here, for the NO, you'll notice that we've got a couple of consistent values here, and so that will allow us to compare the concentrations of oxygen. We'll just do this one thing at a time here, though. Okay, so there's our table. I put it up in the top right-hand corner so we can sort of follow along here. So our rate law, the first one we're going to look at is going to be the oxygen one. So we've got rate 1 on the bottom over rate 2, and I guess it really doesn't matter which way you go with this. It's probably better to have the bigger numbers up top so that you end up with whole numbers in the end here when you go ahead. So we're looking at the ones where the NOs are consistent. So we're looking at this trial and this trial here. So the values we actually need are going to be that number, that number, that number, and that number. Really, it's just a matter of putting these values in. So there's our rate law simplified down. This is this here. And now it's a matter of putting our values in. So our second rate there, that number is gone there. Our first rate has gone there. And then our concentration of oxygen would be there, and our concentration for the first trial is there. So there you go. So it's really just putting it all together, and then it's simplifying it down. So we're going to divide these two numbers together, and we get the number just about 2. And then you divide these two numbers down, and you actually get 2. And then it's just a matter of sort of changing this around so the exponents match. So essentially we've got 2 equaling 2 here. So really it's like saying we've got 2 equaling 2, so that must mean, you know, power of 1, m must be 1. So the exponents were reduced down there. There's a little bit of fancy mathematics. So you make them both have the same base, and then the exponents are what you go ahead and solve. And so we have a first order reaction here with respect to oxygen. So when oxygen doubles, the rate doubles. Now that's just for oxygen, so let's look at the nitrogen monoxide. So there's our, now we're doing 3 and 1, so we're doing this trial and this trial. We've left out 5, that's fine, 5 would work as well, but you know, we only need to do 1 at a time here. So to be clear, we are going to be using that number, that number, that number, and that number. Again, it's just a matter of putting the values in. There's the rate law simplified down. The oxygens are gone. They're constant. Plug your values in. So there's your third rate there, rate 3, rate 1 on the bottom. On the other side, we've got the value here, there, and then that value is there. Now when we simplify this one down, we get this side here reducing down to 4, and we get this side here reducing down to 2. So, you know, you could say that this is, 4, so it's 4. And then you could rewrite that as a base of 2, so it would be 2 to the 2, that's a horrible 2, equals 2 to the n. So your exponents are going to be 2 and n equals 2 there. Hopefully that's not too complicated. They're all kind of similar anyway. So we've got a second order reaction. So when n doubles, the rate quadruples, because it's that squaring effect, right? We've got it squaring, it's just not multiplying by 2. And so we actually have a third order rate law. We got a power of 1, a power of 2 makes it an overall rate of 3. Let's take a look at another example here just to even clarify this a little bit more. So we've got, we're going to try to figure out our rate law. There's our values. So our data's a little more simple this time. So again, we're going to have the same plan. We're going to go ahead and go through and sort this out. Same method. So there is our rate law, and you can flash back to the data. Perhaps I should have put it up here. I did not. And so this one simplifies down to, you write 16 as 4 to the power of 2 equals 4m. And so that's why m equals 2, right? The exponents are equal to each other. And you can double check this one for the other one. We've got 1 to the power of n. So n is 0, right? Because anything raised to the power of 0 will be 1. So 1 equals 2 to the power of 0. N equals 0. And we have a second order here. We've got a 2 and a 0. Okay, so there you go. You can go back, like I said, and double check the data if you don't believe me. So last thing here is to determine the rate constant. So the rate constant K is specific for a particular reaction at a particular temperature. So all we've done here is we have rearranged the equation, because remember, it starts off by giving your rate as equal to K times, all the bracket stuff. So we've just rearranged this here. So we've got K equals rate 1 divided by our rate law, if you will. And then it's just a matter of getting the data together. So there is your first, there's rate 1, and then there's that concentration. And then kind of away you go. So the units for K depend on the order. The units do get a little wild here. You'll notice there's been some unit cancellation. We got a 1 and a 1 there. So, that's going to reduce down to some 2s, and then they're brought up to the top here. In terms of units, these are the units. So I guess this could sort of help you spot some information in the future, or you can just kind of refer back to this when you start to do some questions and determine your rate laws.